the speakers. So I also want to thank you, Jun, for the beautiful introduction to the FMOV effect. I'm going to use effective field theory, which is a technique based on field theory, understandably, right? But as I'll try and explain, effective field theory is a very natural tool to analyze these systems with a large separation of scales. And in particular, the goal in this talk is to quantify range corrections to the phenomenon which I will classify as universality. So to introduce the notion of universality, I thought we would start with a quote from Lewis Carroll. In Alice's Adventures in Wonderland, she encounters, as most of you I'm sure know, the March Hare and the Mad Hatter. And the Mad Hatter asks her a riddle during this crazy tea party that they have. Right? He asks her, why is a raven like a writing desk? Right? So the question that I wanted to start with when I started working in this field is, why are these diverse systems like one another? So the diverse systems are cold atoms, which we've heard a lot about this last few days, few-nucleon systems, which I will allude to briefly without spending very much time on, halo nuclei. So these are nuclei with neutron densities that extend far beyond the proton density, and recently discovered molecules like this X3872. So these are so-called hadronic molecules where you have two mesons which form a bound state whose size is much larger than the size of either of the mesons themselves. And of course, most of you know the answer to this question, and if you didn't, you could read it at the top of the slide, right? So universality, in the context of this talk, will refer to the fact that systems where the absolute value of the scattering length is much larger than the length scale of the interaction share certain common features of their low energy dynamics. By low energy, I mean wave number of order 1 over A, right? So in all of these systems, there are different things that can get measured with more or less trouble, right? And the argument here is that all of these observables bear signatures of the large scattering length. All right, so here's the plan, right? So I'm going to begin by talking about how you set up an effective field theory for a two-body system with large scattering length. And after that brief introduction, I'll talk about results in the three-body system as a function of energy, in order to sort of warm us up, not in the sense of Jun's talk, but sort of in the sense of intellectually warm us up. We're going to talk about an application that I think some of you will be familiar with, which is dimers and trimers of helium-4 atoms. And then we'll look at what happens when you take this analysis and extend it to systems, the systems that we've been talking about this week, in which the scattering length is varying. And then if time permits, I'll say something about the four-body system from the perspective of these connections between nuclear physics and atomic physics. Okay, so let's talk about universality for two bodies. By definition, if we're interested in universality, that means that we're looking at systems for which the details of the interparticle potential are not important. So I'm going to use something very simple. As simple as you can imagine, I'm going to use a delta function interaction, and the strength of this will be parameterized by this number C0. Now, what you're going to do is fix this number C0 by looking at the strength of zero energy scattering. So that means if you know the scattering length, you can fix the value of C0. So you have one experimental parameter, one number in your theory, and that's all. Now, if in the regime where the momentum is of order the inverse scattering length, and that's much larger than the typical length scale in the problem, then quantum corrections matter, and so you can't just stop at Born approximation, right? You have to calculate the whole scattering amplitude, and then you obtain this two-body T matrix. And this is, if you take the limit that A goes to infinity, it's easy to see that this gives you the unitary limit that provides access to so much interesting physics. So one sort of almost trivial consequence of universality here is that this thing has a pole for this wave number equal to I upon A. So that means that if A is positive, there's a two-body bound state, and the binding energy is related to the scattering length. the radius of the the matter radius of that bound state is related to the scattering length. All the properties of that bound state are at this level of approximation related to the scattering length. But this is obviously only an approximation, right? So the subject of this talk is how do you systematically correct for effects beyond this term in the T matrix. So 64 years ago, right, Beta wrote down the effective range expansion for k cotangent delta, right? So this is S-wave scattering, and this form is valid for momenta that are smaller than 1 over L, right? So then in systems where A and L are well separated, there is a wide range of momenta in which this form of the T matrix provides a useful parametrization of the physics. Now, the typical situation in scattering problems, as I'm sure many of you know, is that this effective range is of order the underlying length scale of the potential. So for atom-atom collisions with a van der Waals short-range force, it will be of order the van der Waals scale. So I'm going to assume that this effective range is much smaller than the scattering length in absolute value. So then you have to ask, so what are we, the effective range expansion is an expansion of the real part of the inverse of T. So what am I going to be expanding? It turns out I'm going to expand T in powers of R upon A, or equivalently KR. So this is an expansion for the amplitude itself, and it's valid as long as R is less than A, and as long as KA is less than 1, it's R upon A, and as long as KR is less than 1. So when those of us who work on this problem think about this physics, we're motivated partly by the nuclear physics context. We tend to say that K and 1 over A are of the same order. So obviously you don't want to do this if you're going to go all the way to the unitary limit, but there's a wide range of scattering lengths for which this is useful. But you're not really assuming you can count these separately if you want to. And then the real expansion is in powers of R, with the dimensionality balanced, as I already said, by K or by 1 over A. So this is the leading order term in the expansion. This is the one I discussed on the previous slide. This is next to leading order, and then you can keep going to higher and higher orders. In fact, as long as you have the effective range and the scattering length, you know the first 3 terms, leading, next to leading, and next to leading in that expansion. So for two-body observables, this is nucleon-nucleon scattering data. I know it doesn't look like data, so the data here is actually parameterized by this dashed line. This is the leading order in the expansion. The next leading order is the short dotted line, and the n squared LO result is the black line. So there's convergence to the data. This is really just a consequence that the effective range expansion is working. So the power of this method in the two-body system is that you can relate this to properties of the two-body bound state, which in nuclear physics is the deuteron. So you can calculate, for instance, the deuteron polarizability. This should be R, right? So this expansion in rho gamma is really the expansion in R over A, and this series converges very well, and it converges to the experimental number. So polarizability, not of an atom, but of a nucleus, right? But this is a long-distance observable that's very well understood in the context of an effective field theory, which is an expansion in powers of R upon A. So the other place that you can go, other than electromagnetic observables in the two-body system, is onto higher body systems. So the three-body system was analyzed by Badaki, Hammer, and Van Kolk in 1998. So what the simplest thing you can do is take the leading order T, the one with just the scattering length and unitarity imposed, and compute, let's call it atom dimer scattering, since this is the context that we're particularly interested in this week, right? So you compute atom dimer scattering. So the amplitude in this theory is just going to be the sum of all atom exchanges between dimers. So you sum up this set of diagrams, and you would get, this is an infinite set of diagrams, but you can resum them as an integral equation, and that integral equation includes this term here and this term here. So this big T is the atom dimer scattering amplitude now. So what was discovered straight away, and turns out had been known from the Russian literature for many years previously, right, is that if you just take these two terms and you impose a momentum cutoff on your loop integration, the results are extremely sensitive to the cutoff, and there is no physical prediction because that cutoff is not something that you're just free to play with in this approach. Well, you are free to play with it, but when you play with it, the answers shouldn't change. As Matt said on Monday, we're trying to describe the universe, not some model we made up, and so you want the physics to be insensitive to the cutoff, which really represents the boundary between the physics you included explicitly in your theory and the high energy degrees of freedom that you've subsumed into your contact interactions. So to stabilize this equation, we add a atom-dimer contact interaction. So this means introducing another parameter into the theory. You add an atom-dimer contact interaction, and then you solve the integral equation where the interaction is given by a long-range potential due to the exchange of an atom between dimers, and a short-range potential, which is the contact interaction between the atom and the dimer. So this is the equation, and this is a modified form of one written down by Skorniakov and Termatorisian in 1957. This has continuous scale invariance if h is 0, h being this additional parameter that describes the strength of the atom-dimer interaction. And if h doesn't equal 0, that continuous scale invariance is broken to a discrete scale invariance. And if this sort of S0 log behavior looks familiar, it should. This is the momentum space version of the behavior that Yujun was showing in hyperradius. Right? So here it's in the here it's a momentum space wave function, essentially, right? And this Q is the relative momentum between the atom and the dimer. So this is the behavior that pertains in the regime where the momentum that you're probing in the atom-dimer wave function is much larger than the low momentum scales in the problem. But this discrete scale invariance has the consequences that we all know and love, namely the Efimov effect, because if you take Q and multiply it by e to the 2 pi divided by S0, you get back to the same atom-dimer wave function. And we'll talk more about consequences of that in about 10 minutes. Right? And it also has, but there's another consequence here which it's important to point out, which is that the extra parameter h has been transmuted into this lambda star, and this parameter has to be fixed from a three-body datum. So what this means is that it's not enough just to know the two-body scattering length to predict the properties of the three-body system. And I should say that here I'm talking about bosons, or the same results apply to 3 fermion systems, or indeed any number of if you have any number of fermion degrees of freedom where you're not constrained by statistics. So if you're talking about bosons, then it's not enough to just know the scattering length. You also need one three-body datum to fix the three-body amplitude. But once you know that, you know the three-body amplitude for all momenta within the domain of validity of the effective field theory. So this enables you to predict. So if you take that one three-body observable, you can predict other three-body observables. So this was one example, which this is drawn from the Brutton and Hammer review in 2006. So this is the ground state energy of the helium-4 trimer. This is the first excited state energy of the helium-4 trimer. And the point here is that if you, say, use the three-body datum to fix this observable, then you predict this observable. So by doing this several times over, you have a correlation line. And this correlation line there's just a parameter lambda star that changes as you move along here. And in fact, what Bratton and Hammer did was to plot the results of different microscopic potentials for helium-4 interactions, and they showed that these all fell on this one parameter curve. So that means that all of these models have the same long distance physics. They differ only in their short distance physics, and once you fix that by saying what the energy of the excited trimer is, you understand what the energy of the ground state trimer should be. As I said, this is true for any three-body observable, so that means if you fix the energy of the excited trimer, you can also predict the atom-dimer scattering length. There are also correlations between the three-body and the four-body system, and we'll come back to that, as I said, if time permits. So that's leading order. So now you'd like to do corrections in range divided by the scattering length. So in order to do that, what you do is you insert that range correction in the two-body amplitude in perturbation theory between your leading order wave functions. So in the way we draw our diagrams, that leads to this diagram here, just the top one, is the insertion of the first order part of the two-body T matrix between the leading order wave functions. And if you write that down, you have this fairly simple looking integral. But that fairly simple looking integral, you already know how this behaves at large momentum. So if you analyze the large momentum behavior of this integral, you discover this has a linear divergence. So that means that this answer that you get from this diagram alone will be completely sensitive to the separation that you put between the low momentum modes and the high momentum modes in your theory, and you don't have a prediction. But that's this you address by adding a contact interaction, which we call H1, right, and that gives this set of diagrams and this integral. You might think this means that there's another parameter in the theory, but it's not so. Well, I mean, there is another parameter, but it's the combination of H0 and the range times H1, which you're going to fix from your one three-body datum. So there is no additional three-body datum needed at next to leading order as long as you work at fixed scattering length. So this is the conclusion from this analysis of next to leading order. There should be a prediction for the next to leading order shift as long as you work at fixed scattering length. So in 2006, Lucas Platter and I analyzed this for the helium-4 correlation lines. And so this is leading order is this dot dash line, and next leading order is the dash line. And these are two different microscopic potentials for helium-4 interactions. And you can see that if you include these next to leading order corrections, this does an excellent job of describing both results. And again, this is just because this shows that the difference between these two is just due to short distance physics. And once you say what number for B31 that produces, you can predict what the atom dimer scattering length should be. I should add that this actually gives you a diagnostic, because these were some not at the time published calculations for a atom dimer, and it turned out that these were not fully converged, and you can actually see this straight away from this plot because they don't lie on the correlation line, and no amount of R over A corrections is going to get you to them. So this had to do with the fact that it was difficult to converge the calculations for such a large atom dimer scattering length. So here's a table of results at NLO. This is basically just a tabular form of what I've already been talking about, although here I also show the result for the ground state trimer. And also we can predict the atom dimer effective range. And this is here it's written, this should be inverse gamma, right? But here it's written essentially in units of A, the units of the two-body scattering length. And you can see that all of these numbers seem to converge fairly well, although this one we'll come back to because I would say that this is a little bit deceptive. From the point of view of this theory, this deep state is actually right at the edge of applicability of the theory. The two different results here come from whether you take the atom dimer scattering length as input or the excited trimer as input. But by the time you get to next leading order, it doesn't matter. Okay, so now let's do one more order. So let's do n squared LO. So this is an analysis that I did with my PhD student Chen Ji. And there are many diagrams at n squared LO. There's the one where you include the second order correction to the two-body T matrix. There are three-body force effects of order the square of the effective range. There are iterations of the first order two-body T matrix. There are iterations of the first order three-body force. And there are mixed terms like this. So Chen, who is excellent, computed all these diagrams. And after all that, we discovered that this is the key diagram. So this is the one with the two-body, and I'll explain why it's key on this slide. This is the one with the insertion of the order R squared piece of the two-body T matrix. So it looks like that. And if you analyze it, it has a quadratic divergence. That's fine. You're just going to absorb that. That's the R squared piece of H0, if you want to think of it like that. It's just going to be fixed by the one three-body observable you're already adjusting to. But there's another divergence that's proportional to energy. So this means you need an energy-dependent three-body force to absorb that lambda dependence in your calculation. So that's done by these diagrams, which have this form. And if you don't do that, there's no prediction from the effective field theory. So this is the result that we got, right? So here I'm showing, this plot requires a little explanation, right? So here I'm showing the energy of the excited trimer when you fix the atom dimer scattering length. So green is leading order, red is next to leading order, and blue is n squared LO. So these are the different pieces of the energy with the effective range divided out. And this is versus cutoff. So you see that everything's stable at this order, but if you don't add this additional piece of short distance physics, there's no prediction at n squared LO. There's significant cutoff dependence. So we added this additional input. So that means at n squared LO you need to take 2 inputs. You can then predict the atom diameter effective range. That's these numbers here. What you discover is that there are significant consequences at n squared LO for the deep state, which is why I said this is sort of right on the edge of applicability of this theory. But there are correlations between all the low energy observables. So for instance, the phase shifts are predicted to better than 0.2%, number we got by analyzing the convergence pattern of theory at n squared LO. And this, something similar had been done before for the neutron-deuteron system, again, emphasizing the connection to nuclear physics. So this convergence is really very good because in the helium-4 scattering system, R over A is a number of order 7%, right? So this NLO correction is already fairly small. All right, so now let's move on and talk about three-body data for cold atoms. So as many speakers have already done, I'm going to show this slide with the Efimov spectrum, right? And so here this is plotted as a function of gamma, which in my notation is meant to be the binding momentum of the dimer if it exists, or it's the position of the pole of the virtual state on the negative scattering length side. So here versus 1 over A, you see these trajectories of the Efimov states as a function of 1 over A. So this is the unitary limit here. This is the atom dimer threshold. So when the states vanish through threshold, you have the atom dimer resonance, which I'm going to denote by A star. So that's the scattering length at which that happens. When the states vanish through the three-body threshold, you have a three-body recombination maximum to these deep dimers that were being discussed in the previous talk. And there's also a point somewhere out here where the atom dimer T matrix goes to 0, and that produces a recombination minimum. So as has been mentioned by several speakers already, the fact that there's one three-body parameter at leading order means that all these features are correlated. And this is what we call the universal relations between, say, once you know the position of the recombination minimum, universality predicts the value of all other, the position of all other features. Just as once you fix the position of one of these three-body bound states, you've also fixed the position of all the others, and you've fixed how they depend on 1 over A. But, and this is the difference between the black curve and the red curve, the positions of all these features are going to be shifted by effects of order R upon A. Right? And so that's what I'm going to talk about in this part of the talk. I want to emphasize that the discovery of the last couple of years that in a variety of systems, A minus is approximately -9 times the van der Waals length scale. This is not a universal relation in the sense that I'm using the word universality in this talk, right? So I'm going to call this, if we need to have a discussion about it, I'm going to call this van der Waals universality, right? So for instance, in nuclear physics, we don't have this because we have a different short-range potential, right? So, but it is certainly interesting that for a variety of atomic species, this relation seems to hold experimentally. So in this context, I'm going to appeal to another quote from Lewis Carroll, right, which is that when I use a word, it means what I choose it to mean, neither more nor less, right? To which some of you may respond whether it's really true that I can make words mean whatever I want. Well, and the answer is that the question really is just who is to be master. Okay, so the technology to compute the R over A corrections to recombination features is exactly the same as I've already introduced. You just do this first-order perturbation calculation. So we've already seen this integral once in the context of the helium-4 trimer system. So here I'm interested in dimer atom scattering, but with varying A. But there's an important difference if A is varying, which is that this divergence, which is logarithmic in the cutoff, now has a parameter that's varying. So you can absorb it at one value of the scattering length, but when you move to a different value of the scattering length, your answer will change by an amount that is proportional to the logarithm of the cutoff, which means that you don't have a prediction anymore. So what's the implication of this? It means that there has to be a piece of the short-range physics. In this approach, it's a three-body force, but fundamentally it just means that there's some short-range physics in the atom-dimer system that is A-dependent. So if you go to look at range corrections, it's not enough to just know the effective range. You need to also know this one additional piece of three-body physics that tells you how the short-distance physics in the problem changes with scattering length. Once you know that, the rest of the A-dependence is driven by long-distance physics and is predictive at this order. So here is a plot, and here I've just used the famous cesium data of Kramer et al. Right, here's a plot of the recombination length, and just for fun, I renormalized to the recombination 0. Here I picked this one at large scattering length because the things are more stable in general the larger the feature you renormalize to, right? And that's the red line at leading order. And next to leading order, I need two three-body inputs. And so I arranged to keep this in basically the same place, and then I fixed this to A minus somewhere. It's actually infinitely far in that direction because this is a log scale. And so you see that this feature here, the recombination minimum at smaller a, shifts markedly because of those range corrections that we're discussing. And there are two effects going on here. There's an effect due to the long-range physics in the atom-dimer system, i.e. due to the atom-dimer effective range. And there's an effect due to short-distance physics, which here you've set by using this additional input. I should add that here, this plot shouldn't be taken as a prediction for what you're going to measure if you go out this far in A, because I haven't included the kind of finite temperature effects that can be calculated in either hyperspherical formalism or in effective field theory. And I haven't included deep dimer effects. Right? This can be done. It just hasn't been done here because what I was focusing on was the positions of the features. So if you're interested in the positions of the features, one might look, for instance, at a set of experimental data like this from a recent paper by Dyke et al., right, and extract the positions of the features. Well, they extracted the positions of the features, right? So this is the atom-dimer resonance. This is the recombination minimum. These are on the positive A side. And this is the recombination maximum on the negative length, on the negative A side. So what I'm going to do is say that this one and this one have been measured, and I'm going to predict the position of this one. Right, so I need two three-body inputs. So I'll take this and this as my three-body input, and then I'll predict the position of the third feature. So here's what we call semi-universal relation. In this semi-universal relation, it's important that the effective range also varies with a scattering length, but this can just include this straightforwardly in the calculation. So if you know, and so this taken from the same paper, how the effective range varies as a function of the scattering length, you can just put that in and include it in the computation. So before I apply that to the Dyke et al. Data, let me apply it to the slightly older data from the Tel Aviv group. So they measured minima and maxima at these positions. And from a theory of the Feshbach resonance, we obtained these numbers for the dependence of the effective range on the scattering length. So we plugged those into this semi-universal relation and obtained this prediction for A star if we use the recombination maximum as our leading order input. We obtain this prediction if we use the minimum as our leading order input. And so by averaging these and taking the difference as a measure of the uncertainty, we have this prediction for the atom-dimer resonance. So after we published this, Gross et al. Published a subsequent paper with their experimental results on this, and this is entirely consistent within error bars with the prediction from this analysis of range corrections. So what I want to point out, right, is that this number is significantly different from the universal prediction, which is one of these two numbers depending on what you take as input, but the range corrections shift it in the right direction to get agreement between theory and experiment. And the same is true if you look at the Dyke et al. Data. So the minima and maxima as extracted from that figure I showed are located at these positions. I haven't propagated the errors here, but this can be done straightforwardly. If you take the calculation of the effective ranges in this system, which is now MF equals 1, as input, then the effective field theory prediction looks like this with one input, like this with the other input. So these numbers here would be the universal result, the one from the universal relations, but range corrections tend to shift this number upwards, and they shift it up by enough that there is some agreement with the data. There's a little bit of tension here, but I would say it's at this point there's no inconsistency. All right. So Seth is standing up. So let me summarize the results on recombination, and then I have one overall summary. I'll just do this rapidly here. So the goal here was to diagnose effects beyond universality that are sensitive to the effective range. And the point I want to make in particular is that it's not enough in this approach just to know the effective range. You also need a second three-body datum if you want to predict the A dependence. But this leads to these semi-universal relations, which you can apply to, the relations are universal. Once you know A and R and the position of two features, you can predict the third feature no matter what system you're looking at. There are some interesting things to look at in the future, and one very interesting subject would be to look at whether there is a similar correlation between, as there seems to be at leading order, between the short distance physics in a variety of atomic systems, also for this additional parameter at next to leading order. So I'll skip this because, to quote Lewis Carroll again, time is not my friend, right? So in this little quote here, which you can read for yourself, Alice accuses the Mad Hatter of wasting her time by asking riddles that don't have an answer. And it turns out it's really true that Lewis Carroll had no answer in mind when he wrote down this riddle. But the Mad Hatter responded that time is his friend, but time is not my friend because we're done. And here are my conclusions, which you can read for yourself. Thank you very much. I'm not quite sure that I understand the question, right? So you're talking about whether you go back to the A to the fourth behavior?
Yes, yeah, the A to the fourth behavior before it converges to the A to the fourth behavior. They have a feature and then...
Yeah, I mean, so I have taken the numbers from these papers at face value, right? So I have not made any attempt to analyze why the recombination data look the way they do as a function of energy. This too is something that could be done within this framework, right? In principle, you have all the low energy thresholds and resonances which tell you how these recombination data should look as a function of scattering length, right? But I have not done this here, right? As I said, right, the first thing to do to see if these semi-universal relations were working or not was to take positions of features that had nominally been extracted and see if the patterns of those positions was in agreement with the predictions from the range corrections, which it seems to be. So, yeah. Yeah. Right, right. Yeah, so I mean, I think what I would say is that he's seeing that range corrections are important, right? You're talking about the two-body resonance, right? So it's simply for understanding the binding energy of the shallow dimer, right? There comes a point, right, and it's clear already from, I hope I said this in my conclusion, right? There comes a point at which an expansion in R over A doesn't work anymore, right? So if the dimer becomes sufficiently deep that its binding momentum is of order 1 over R, then you're completely sensitive to the short distance details of your model, right? So my comment would be, yes, range corrections are important, and yes, if you go far enough away from resonance, then the details of your model will matter, right? Gamma equals 1 over A is only going to work very close to resonance, and as the dimer gets deeper, gamma will be, what is it, like 1 over A plus a half R over A squared. And then once the R over A expansion doesn't converge anymore, gamma will be whatever it is in the model of the two-body potential that you happen to have used. Does that answer your question? Yeah.
I was wondering if you had any comments on the recent Roy and Magugno preprint. I don't know if you've seen it, which seemed to have evidence that it's more the van der Waals length than the effective range that matters, because they see the same universality now for 7 features, 7 FMR resonances in potassium, bosonic potassium, and they all seem to fit the pattern of the van der Waals length, whereas even the narrow resonances have a very different effective range.
Yeah, I mean, I think this is really interesting, right? So this would be a statement about leading order, right? So what I can, so I mean, that's this, well, it's not this point down here, right? But I mean, I think understanding how the leading order 3-body parameter emerges out of the van der Waals length scale is a very interesting connection between different ways of looking at the physics in this problem. What I can say is that at next to leading order, oh, sorry, wrong way. So we have this relation for the corrections, right? And if you just take fixed effective range, it doesn't work, right? So it's in this context, it's actually very important that the effective range varies across the resonance if you want to understand the pattern of range corrections to universality, right? So, I mean, this is a marked variation in effective range across the resonance. So once you start looking at corrections in this regime where R over A is less than 1 but not really, really small, then there's one important point is that R over A, you know, R has one value here and it has a completely different value over here. So this shows up in this formula and affects the predictions.